Okay, first of all, I would like to thank the organizers for organizing this conference and also for giving me the opportunity to speak here. And yeah, welcome to the first of my two talks about ribbon cobordisms between length spaces. So I'm going to start by giving you the definition, what it means for two links to be concordant. So if we have two links, L1 and L2, in the three-sphere, we say that they're concordant if they co-bound a properly embedded surface C in S3 across an interval, such that this surface has Euler characteristic equal to 0 and doesn't have any closed components. So schematically, in this picture, S3 across an interval is depicted as this cylinder. And in this portion S3 cross 0, we see our first link, L1. On the right, in S3 cross 1, we see our second link, L2. And in between them, there is this surface C that interpolates between them. And if you're used to the sort of standard notion of concordance between knots, where we just require a concordance to be a properly embedded annulus in S3 cross I, so this notion here coincides with that notion in the case where L1 and L2 are knots. And so this is just one way of generalizing concordance to the setting of links, which is the notion I'm using in my paper. So one basic question one can ask is, how can we abstract two given links from being concordant? Like, how can we tell that they're not concordant? And there are obviously many ways of doing that. There's a lot of concordance invariants out there. A slightly different way of doing this is to look at the branched double cover of S3 cross I. So more precisely, we can take this S3 cross I with our concordance C sitting inside it and form its double cover branched along C. So what we get is a four manifold, which I call W here, with two boundary components Y1 and Y2. And these two boundary components actually are the double covers of the three-sphere, S3, branched along L1 and L2 respectively. So W can be seen as a cobordism between these three manifolds. But more is true, namely that the inclusion maps of Y1 and Y2 each into W, they each induce isomorphisms on rational homology. And so in this setting, whenever we have such a four manifold, that is a cobordism between three manifolds, and the inclusion maps have this property as above, then we say that W is a rational homology cobordism. So the point here being that if we have two links and they're supposed to be concordant, then their branch double covers have to be rational homology cobordant. So that can be seen as abstracting the links from being concordant. While this question of sort of figuring out which links are concordant to each other is probably too broad to just ask in general, one can always restrict to certain families of links. In my work, I restrict myself to this family of two-bridge links. So what does it mean to be two-bridge? We say that a link is two-bridge if we can isotope it in such a way that it has exactly two local maxima with respect to some coordinate axis. So in this picture, this is a diagram for the right-handed trefoil, left-handed actually, and we can see that with respect to the horizontal axis, clearly this diagram has two local maxima. So the trefoil knot is a two-bridge knot. What's more, I'm going to be talking about length spaces. So these are, from the perspective of, for example, Hagar genus, these are the simplest three manifolds out there other than S3. And I go by the definition for the purpose of this talk that the length space LPQ is the oriented three manifold that is obtained by performing P over Q framed den surgery along the unknot in S3. And what's the connection between these two concepts? So the point is that two bridge links, they're precisely those links whose branch double covers are length spaces. And both of these, the family of length spaces, but also the family of two bridge knots, they're both parameterized by pairs of co-prime integers P and Q, usually chosen in such a way that Q lies between 0 and P. And they're parameterized in such a way that LPQ is precisely the branch double cover of the 3-sphere branched along the 2-bridge node KPQ. So there's a nice correspondence between these parameters. Okay, so restricting ourselves to this case, then the initial question then becomes, how can, if we want to abstract 2-bridge links from being concordant, passing to the double branch cover of a concordance, well, the question then becomes, how can we abstract or determine when there exists a rational homology cobordism from one lens space to another? And this question actually was completely resolved by Liska in 2007. And in this first part of the talk, I'm not going to get into his methods, but I'm just going to say for now that he used a lattice theoretic abstraction. So a lattice, very briefly, is a free abelian group that, so it's a group isomorphic to Z to the n for some n, that is also endowed with a symmetric bilinear pairing, so sort of like an inner product. And this abstraction he used is very combinatorial in nature. That's sort of the thing I like about it. And so, yeah, I'm not going to give you the full statement of his result, but sort of the gist of it, or the core of his statement, basically is that he determines sets fancy R and fancy F sub n for n greater than or equal to 2. So these are sets of rational numbers. And the first one is basically characterized by the property that a rational number P over Q belongs to this set R precisely if the corresponding lens space, LPQ, is a rational homology cobordant to the 3-sphere. In other words, bounds a rational homology ball. Whereas these other sets, F sub n, these are characterized by the property that if a rational number is an element of that set, Fn, precisely if LPQ is rational homology cobordant to the special lens space Ln, 1. So in particular, any two lens spaces whose fractions both belong to R, say, or both belong to F sub n, they're going to be rational homology cobordant, because if, say, both fractions belong to R, we can just take a rational homology cobordant from the first lens space to S3, and then from S3 to the second one. And all in all, we get a rational homology cobordism between these two lens spaces. And similarly for F sub n. And yeah, as a corollary, Liska was then able to completely resolve the very initial question, which is to determine when two bridge links are concordant to each other. Because while this can be seen, his result can be seen just purely as a result concerning rational homology cobordism between lens spaces, since we can, given concordances, construct rational homology cobordisms between their branch double covers, this led to also a complete classification of when exactly two bridge links are concordant to each other. Now, I'm going to move a little bit, shift focus a little bit more towards my work. So what I was looking at were more special concordances, which are ribbon concordances. So we say that the concordance C from a link L1 to another link L2 is ribbon if it has no local maxima with respect to the second coordinate of S3 cross an interval. So again, schematically here we see a concordance C properly embedded in S3 cross an interval. And now you can see, unlike in the first picture, if you remember, the first picture had sort of an additional cusp. In this picture, if we sort of traverse the concordance or S3 cross I from left to right and keep track of what portion of the concordance we see, we only ever see stuff appearing. We never see stuff sort of dying off or disappearing. So that's what it means to have just local minima, but no local maxima with respect to the second coordinate on S3 cross an interval. So this is a schematic picture of a ribbon concordance. And yeah, so one might wonder, how can we come up with an abstraction similar to the first one involving these branch double covers? And it turns out that if we have a ribbon concordance from a link L1 to L2, then actually passing to the double branch cover of S3 cross I branched along our ribbon concordance, then that four-manifold, that cobordism, admits a relative handle decomposition relative to the double branch cover of the first link that uses just 1 and 2 handles. So we can start out with the double branch cover of the first link, attach just 1 and 2 handles, and build this whole double branch cover of S3 cross an interval branched along the ribbon concordance. So typically, four-dimensional cobordisms will always involve 1, 2, and 3 handles, but here it's, the fact that this concordance we started out with, this ribbon, is reflected in the fact that 3 handles are not needed. So this led Daemi, Lidman, Velevik, and Wong to a corresponding notion, refined notion of rational homology cobordisms. So according to them, a rational homology cobordism W from Y1 to Y2 is also said to be a ribbon if W just can be built from Y1 cross an interval by just attaching 1 and 2 handles. So no 3 handles allowed. The nomenclature comes from what I just said above, that if we start out with the ribbon concordance, we actually obtain a ribbon cobordism from the double branch cover of the first link to the double branch cover of the second link. And lastly, just a bit of notation. So if there exists a ribbon cobordism from our 3-manifold Y1 to Y2, then we write that Y1 is less than or equal to Y2. And as this notation suggests, this notion of ribbon rational homology cobordism is not symmetric, unlike the notion of just usual rational homology cobordism, which I guess makes sense, because if you have 2 3-manifolds and you can go from one to the other by just attaching 1 and 2 handles, probably wouldn't expect that you could also go from the second to the first one, like in the other direction, by just attaching 1 and 2 handles. And then a naturally arising question in this, with this being said, is the question: when does there exist a ribbon rational homology cobordism from a lens space to another lens space? So we know when there exists just the rational homology cobordism between 2 lens spaces, but when can this rational homology cobordism be realized by a ribbon cobordism? And so the way one can attack this question is to basically take Liska's obstruction and promote it to an obstruction not to just rational homology cobordism, but rather to an obstruction to ribbon rational homology cobordisms. So as I said, I'm not going to get into the details of his or this obstruction, but essentially it builds on his obstruction. It's just sort of like tweaking it a little bit or promoting. And with that result obstruction at hand, I was able to prove that if we do have 2 lens spaces, LP1Q1 and LP2Q2, and we're just going to assume that P1 and P2 are not the same here to sort of exclude the sort of trivial cobordism, the product cobordism, which is just LP1Q1 cross an interval. If there exists a ribbon cobordism from the first one to the second one, it turns out that the first lens space actually has to be up to orientation homeomorphic to this special lens space Ln(1) for some n greater than or equal to 1. So as a converse to this, I chose not to include this in my theorem because it sort of comes out of Liska's work. Conversely also, that if n here happens to be 1, so we were looking at L1,1, which is just S3, then any lens space that is rational homology cobordant to S3 actually can be realized, or any such rational homology cobordism can be realized by a ribbon rational homology cobordism. And similarly, if n is greater than or equal to 2, so if we start out with Ln(1), there is a ribbon rational homology cobordism to any other lens space that even stands a chance at being rational homology cobordant to Ln(1). One way of interpreting this, of course, is that sort of most rational homology cobordisms between lens spaces are actually not ribbon, so they can't be realized by a cobordism that doesn't involve 3 handles. For example, take any 2 lens spaces that are rational homology cobordant to S3 but aren't S3 themselves. So they are rational homology cobordant by Liska's work, but they're not going to be, there isn't going to exist a ribbon rational homology cobordism from one to the other. And similarly, in the case where we're looking at length spaces that are rational homology cobordant to ln, 1. And yeah, without stating this, because it's a little messy, I'm just going to mention that this result actually can also be extended to the case where we're looking at cobordisms. That's the same as Liska. He also extended his results to cobordisms whose boundary components aren't just single length spaces, but connected sums thereof. And in a very similar way, I was also able to extend this above result to the case of, or to determine when does there exist a ribbon rational homology cobordism from a connect sum of consisting just of length spaces to a different three manifold that is just a connected sum of length spaces. And again, similar to Liska's work, this result has sort of a natural corollary on the level of two bridge links, and it's really analogous to the statement about the length spaces. So namely, if we have a two bridge link KP1Q1, and that's supposed to admit a ribbon concordance to a different two bridge link KP2Q2, where again we assume that P1 and P2 are not the same, to sort of exclude trivial occurrences, then again it turns out that the first two bridge link has to be of the form Kn, 1 for some n greater than or equal to 1. And again, there are these converse statements, namely that if we do have a two bridge link that is concordant to K1, 1, which is the unknot, then there does exist a ribbon concordance to that knot from the unknot, and similarly for these other two bridge links belonging to the families f sub n for n greater than or equal to 2. And again, these converse statements, they were at the very least implicit in Liska's work, so that's why I didn't choose to include them in the corollary. So my work really mainly sort of obstructed any other possibility of there being ribbon cobordisms or ribbon concordances between length spaces and two bridge links, respectively. And yeah, again, we can paraphrase this result to say that any ribbon concordance between two bridge links actually has to start as at a two bridge link of the form Kn, 1, which happens to be the T2, n torus knot. So again, typically, if you're given a concordance between two bridge links, chances are low that that's going to be a ribbon concordance. So one of the two has to be of this very special form. And this, of course, then yields infinite families of two bridge links which are concordant. Similarly to the length space case, it yields infinite families of two bridge links which are concordant but not ribbon concordant. So it yields infinitely many infinite families. And similarly to the length space scenario, this can again be extended to the case where we're looking at links that are connected sums of two bridge links. So I was able to determine when exactly does there exist a ribbon concordance from a connected sum of two bridge links to another connected sum of two bridge links. And yeah, this is all I have to say for this sort of statement of results, part 1 of my talk. If you're interested in the details involving lattices, how exactly this all works, I invite you to watch my second talk.